Hey guys, welcome back to Chapter 11, ANOVA. In this video we're going to move into the randomized block, which operates essentially the exact same way as the standard one-way ANOVA, except we add a block variable into the mix. And this block variable adds to our level of accuracy and being able to look at the data. Keep getting emails from students and I'll keep closing them out. But yeah, so we add this block variable into it, and that's going to allow us to kind of filter out some more of the error. So what we did in the one-way ANOVA, we filtered out the error of the treatments and the unexpectable error, and then this, now we're going to be adding a block in. So a block is kind of like just keeping a continuous person for each, or a continuous entity that represents each data point across the table. So that might sound a little bit confusing, but we'll get into the problem and I think you'll see exactly what I'm talking about. Okay, so let's just look at this problem. Take a second to look at this table. The difference between this table and the last one is that we have this new line in for between blocks, and then sum of squares block and degrees of freedom for the block and mean squares for the block. And then now we also have another fcalc for the block now too. So we're going to be getting two fcalc values out of this one as opposed to just one. Okay, so let's read this example and then we're going to compare it to the first example that we did and see if we can kind of glean any information. Example, suppose that we are interested in investigating the possible effect of font type on the number of words read per minute by 3 different readers. Okay, so now if we look inside of this table, we have a total of 12 data points in here, right? We have a total of 12 data points. In our last example, we also had a total of 12 data points. But one thing that we didn't have commonality among some of the data points, right? So in the last problem that we did, the treatment, if you want to look at your worksheet on, I believe, page 1, we had let me see, how many different treatments did we have? We had 3 different package designs. Okay, so those were our 3 different treatments, and then 4 pieces of data within each package design. Or yeah, 4 pieces of data within each package design, and those were test sites. Okay, so those were 12 different test sites. Okay, now we're looking at an ANOVA scenario to where, yeah, these are 12 different data points, but they all stem from 3 readers. Okay, so we have this commonality amongst the reader that is, we're going to then be able to filter out that error. So like, say, looking at this data set, we could run this as just a one-way ANOVA, and it would tend to be less accurate than if we ran it as a randomized block. Okay, because with the randomized block, we know another fact about the data set. We know that, like, for that top line, for that reader 1 line, we have all of those different fonts are going to subscribe to this, or are going to be a part of this person's data set in and of itself. So that's one level of error that we're going to calculate and we're going to factor out of the scenario. Okay, so it's going to give us a more accurate result at the end, a more accurate fcalc, and then we're going to be able to make a more accurate recommendation or more accurate calculation at the end as to whether or not we have some differing means. Okay, so we'll move on past the data, and it says, is there a significant difference in the number of words read per minute across fonts? Use an alpha level of 0.05. Okay, so using the same readers for all 4 fonts should control, using the same readers for all 4 fonts should control for inherent differences in reading speed across individuals. Therefore, readers are serving as our blocks, our control. So just like the last problem, we're going to start with our hypothesis. So we have H naught, and that's mu of courier equals mu of italic equals mu of elite equals mu of script. Right, so we're just saying that, like, our status quo is that the reading speed for all of these are the exact same. So the population reading speed, or the population mean of the reading speed for all of these are the exact same. Okay, so that's our status quo, that's our H naught. HA, our alternative hypothesis, is that at least one of them differs. So, or at least one of them differs from the pack, however you want to think about it like that. So it says here at least two of the average reading speeds are not equal, right? So one is different than the other. Either way you want to write that is fine. I'm fine with either way. Okay, and because we also controlled for the effective number of words read per minute by using only 3 readers, our variability within error can within each font can be further explained by this blocking factor. Okay, so now I'm going to show you how to calculate these, just similarly to the way that we did last time. Fortunately, it's a lot, so I guess I will do it just like before. Okay. So we'll start with SST, or SS total, as we called it last time. Guess we'll use red again. So SST, this is going to be the exact same formula from last time, or not SS total, I'm sorry. SST is going to be SS treatment, okay? They denote it as SS1 here, which is fine. But yeah, we're going to denote it as SST. So this could be a T, and this could be a B. Okay. SST. And this is going to just be okay, sorry, my pen was not doing the right thing. It's going to be the summation of J. Okay. Okay, we're just going to edit back from 715. Okay, sorry, I had to stop there, and now I'm back. So we're writing out the formula for SST, and that's the summation for all j of the number of data points in the treatment times that treatment's mean minus the overall mean. So that's our formula for that. So let's go ahead and run it. And so if we are looking at the data set, so why don't you guys go ahead and look at the data set right now. Let me pull it up as well. So we're looking at, so in treatment courier, we have 3 data points. So we get 3 times the mean of treatment courier, which is going to be 579.3 minus the overall mean, so x bar bar. And it looks like, for whatever reason, on the worksheet they use a different notation, but that's the same as x bar bar. Okay, so that's 530.5 squared. Okay, so now we do the next treatment. So the next treatment over is italic, and there are 3 data points in there. And that mean is 470.3 minus the same overall mean. My pen is starting to not work again. Gotta love it. And so then the next one is elite. 3 data points inside of elite. Its treatment mean is 548.3 minus the overall mean out of that. Square the whole thing, and then lastly 3 times 524, which is the treatment mean for script, minus the overall mean, 530.5. And that ultimately is going to shake out to 19,000 and 93.71, which looks to be pretty close to what they got up here. I assume we're just rounding error or something like that. So whatever you want to do is fine. So 19,095 or 19,071. I'm sure the output will give us the exact number. So that's that. And now we're going to do the blocks. So the SSB. So let me change the pen. See if that changes anything about the way that it's writing. SSB. Now this is just going to be summation for all I of x bar sub I minus, this pen, x double bar squared. Oh, and we forgot to put the little n sub j in there. This is actually going to be n sub I. So that can go on the inside of the summation or on the outside of the summation. It doesn't actually matter. So then we are going to be looking at the mean across the block, so across the reader, so the reader's mean minus the overall mean times the number of data points in that. So looking at reader 1, how many data points do we have? We have 1 in courier, 1 in italic, 1 in elite, 1 in script. So we have 4 data points inside reader 1. So this would be 4 times that mean for reader 1. So 517.25. 517.25 minus the overall mean, 530.5 squared. And then reader 2, there's 4 data points for reader 2. We have 516.75 for that mean minus the same 530.5 all squared. And we add up the last one. We have 4 data points for reader 3, and we have 557.5 minus 530.5 squared. And that all is going to shake out in my calculation to be 4,374.5. Okay, and that, how close is that? That's exactly what they got, so that's good. Okay, so now the next thing that we could do, so we've got the SST and we've got the SSB. Okay, so we've got the sum of squares for the treatments and the blocks. So what we could do is we could do the SSE, so the sum of squares for the error, and we would just use the same formula that we did in the one-way ANOVA. So if you forgot what that is, just turn a couple pages back and you could look there. Or what we could do is we could do the SST, which is just the big general formula. So the big general formula is the double summation, and that's essentially every single data point, so the xi's, so every single xi minus the overall mean. That's probably the one that's most intuitive. There's the least thinking, I think, that goes along with that. So let's just do that, and then we can always minus off the treatments and the blocks to find whatever E is, the SSE, okay? That looks like how this example is set up anyways, so we'll go ahead and do that. So the SSTO equals, let's see here, pen turn back on, equals the double summation of xij minus x double bar, whole thing squared. Gosh, this pen is driving me nuts. Alright, so we get 576 minus 530.5 squared, because 576 is just our first cell. And then the next one is 565 minus 530.5 squared plus 597 minus 530.5 squared plus 453 minus, this pen is killer. Anyways, there. So on and so forth. Okay? So it's going to be the whole data set. So we're going to have 12 of these squares or whatever, and then this is eventually going to equal out to 24,515. So we scroll up. Okay, so they got exactly what I got, which is good. I just didn't want to show all the math. You guys get how to do it. Okay, so 24,515. And then, so let's just find out what the error is. So to find out what the error is, we just say 24,515 minus 19,095 and 4374.5, and that is going to equal 1,045.5. So that goes in here. Okay, now we have to do the degrees of freedom. So the degrees of freedom are between treatments is just going to be p minus 1. So p is the number of treatments. So how many treatments do we have? We have 4 treatments: Courier, Italic, Elite, and Script. So 4 treatments, so it's just going to be 4 minus 1. So 3 here. And then degrees of freedom for blocks are just going to be b minus 1, so the number of blocks minus 1. So how many blocks are there? The blocks are the number of readers. It's 3 minus 1, so it's 2. And then for the total, it's just going to be n minus 1, essentially. Or PB minus 1, either way. And that's just going to be 12 minus 1, so it's going to be 11. And then similarly, we can find out what the degrees of freedom for the error is just based upon minusing. So 11 minus 3 minus 2 is equal to 6. It's very easy to come up with that. Now, all we have to do then is run our calculation. So we have 19,095 divided by 3. And that's going to get us our mean squares treatment, our MST. So it's going to be 6,365. Excuse me. And then now we have to do the mean squares block. That'll be 4374.5 divided by your degrees of freedom of 2, which is going to be 2187.25. And the mean squares error is going to be 6, or it's going to be 1045.5 divided by 6. So 174.25. And we can see from our table that the FCalc is just going to be whatever the mean squares is for, either the treatment or the block divided by that of the error. So the first one is going to be the 6365 divided by the 174.25, and that is going to get us 36.53. Okay, and then the next is going to be our 2187.25 divided by our 174.25, and that is going to get us 12.55. So these are our FCalcs. So we now have an FCalc for the treatment and an FCalc for the block. So now that we have the table all filled out, we now have FCalc values for the treatment and the blocks. And now we need to determine, is this FCalc, are these FCalcs beyond critical values, right? So these are our calc values. Now we need to know, are they beyond critical values? We haven't gotten our critical values yet. So the way that we obtain critical values is we go to the F table, and we are going to be looking for an FCalc or an FCrit that is going to be F of alpha, comma, P minus 1, comma, P minus 1 times B minus 1. So let's see if we can find these numbers in that table anywhere. So P minus 1, B minus 1. If you are looking in your packet, look at the page on the randomized block, and the P minus 1, B minus 1 is the degrees of freedom for the unexplainable error. So the degrees of freedom for the SSE. So we can write that, or the degrees of freedom for the error. So we'll just say DFE. And the P minus 1 is the degrees of freedom for the treatment. Likewise, if we're wanting to compare our critical value of the block, similarly, we would have F of alpha, B minus 1, comma, P minus 1 times B minus 1. Right, so this is going to be F of alpha and the degrees of freedom of the block and the degrees of freedom of the error. And so this is the numerator, this is the denominator, and so similarly numerator, denominator. So let's go to our table. Well, first of all, let's plug in these values. So our P minus 1, B minus 1 is our degrees of freedom error, and that is going to be 6. So this number is going to be 6 in this case. And our B minus 1 is going to be 2, and our P minus 1 is going to be 3. And our alpha is, what did we say our alpha is? Did we define one for this problem? Yes, we did. 0.05. Like always. Okay, so now we would go to our table. And we go to the F table of 0.05. So this is the F table of 0.05. So the numerator on the top and the denominator on the bottom. So the first one that we're looking for, I believe, was 0.05, 3, and then 6. So 3, 6. So 4.76 So F crit, okay, 4.76, and then this F crit is, we look for 2 and 6, 2 and 6, 2, 6, 5.14. This F crit is 5.14. So these would be the F critical values that we would be comparing our F calc values to. So for the treatment, we would compare it to the 4.76, crushes it, right? The treatment is just well above that. And 5.14 for the block, and crushes it. 12.55 is well above. 5.14. So in this regard, we would reject the null hypothesis that all the means are equal in favor of at least one of the means not being equal. And you can look at the output on the last page. Here is some of the megastat output. And we can see we've got all the right critical values, and the p-values are given here. So the output's just going to automatically spit out p-values. Notice the p-value of 0.0003. That reflects the fact that this F value just absolutely crushed the critical value. And then this p-value of 0.0072, and that reflects that it also crushed the p-value, but less so, right? So 36 was far greater than the 4.76, and 12 was far greater than the 5, but not as great, and you can see that that is also reflected in the p-values as well. So then you can run a similar type of two-key analysis. I'm not going to go through it because we did it in the last video. You can run a similar type of two-key analysis or a similar type of pairwise t-tests here that they've done. And yeah, that's that. So that is randomized block. All right, guys, until next time. So the next video will be two-way ANOVA, and that will be that. In the discussion boards, please let me know if you have any questions on anything, and I will be happy to ask them, or I'll be happy to answer them. I'm trying to get these videos out kind of as soon as possible because I just want to give you guys as much time to do these problems. So there may be something that I end up leaving out, but you just need to then figure that out and then ask me the questions, and I'll be more than happy to look into it and answer that question for you. So, all right, guys, thanks for tuning in. Next thing up will be two-way ANOVA, and we're moving. We're almost done with all of the topics in this whole semester. It'll be two-way ANOVA, and then we'll learn the 2 new chi-squares tests, and then that's just it. That's just it. All right. Well, thanks so much for tuning in. Let me know if you have any questions. Until next time.